Let's start with Leopoldo Zayas, who will talk about subleading microstate counting of AdS black hole entropy. Please, Leo.
All right, thank you. Thank you for the invitation to speak at this conference. It's really a pleasure. So what I want to talk about is based on this work that I've been doing over the last couple of years. The first paper here is with a master's student at Cambridge, Yu Xing, and then a graduate student in CISA, Alfredo Gonzalez Lescano. Jung Ho Hong is a student here in Michigan. Jim Liu is my colleague, and other characters that you know very well, Benini, Gan, and again, Jim Liu, and Wen Li is a student in Princeton. So it's good that I got to see a little bit of Magdacena's slides, because this is precisely my first slide is an apology. Why should a black hole talk be given at an integrability conference? And of course, my answer is different. My answer is, of course, because AdS-CFT. So AdS-CFT, as we all know, connects observables in quantum field theory to quantum gravity questions. And that's why I think it makes sense to give this talk. And I will try to convince you, of course, that many of the techniques that I routinely use in integrability are going to be crucial to deeper understanding this black hole. So when we talk about black hole, people like to use the cliche phrase of a hydrogen atom, and in which case, of course, the entropy is like the Bohr energy. So it's the main thing that you have to get right. And I say that this is, the universality of this formula is impressive, right? So it is true for asymptotically flat black holes, for asymptotically AdS black hole, for rotating black hole, for anything is true. So that's great, but that's also a little bit of a curse, because what that means is that there are some explanations that are going to be deep UV explanation, but then there's a sense in which you know that their answer could be obtained just by symmetry principle. So the analogy that I like to keep in mind is a little bit like the black string in a string theory, right? So we are very happy that Strominger and Baffa completely clarified this problem for us from the string theory point of view. But of course, you can also understand the microscopic degrees of freedom just studying symmetries near the horizon and applying the Brown-Henault analysis of asymptotic freedom. So because of that, because of this universality, you are forced to look at correction. So in the correction is where you will find the physics. From very generic, point of view, if you have a gravity formula like the entropy, there will be two kinds of corrections. So once when you are considering Einstein-Hilbert as an effective theory, and then there will be higher curvature corrections. And yesterday we had a wonderful talk by Silvio about interesting structures there. So that's one kind of correction that you will have to string to the entropy formula. But of course, there are also corrections that come, the quantum corrections that come from Newton's coupling. These are some of those are the ones that I want to talk about. So this is very general for any black hole in a gravity theory, but of course we are interested in a string theory, and there we know very, very carefully what are the scales that we have, the string length and the coupling constant. And of course, in this AdS-CFT context, we are going to be discussing or focus on Hopf coupling corrections and corrections that essentially come from the rank. So my goal in this talk is to basically show you that systematically controlling these corrections, which are the place where the physics will be found, is of course will require integrability techniques and certainly some understanding of different Bettian subsets that one needs to write in this question. So that's sort of my apology for the conference. So why now? Now is because there have been important developments in our microscopic understanding of AdS black holes. So one work that I like to highlight is Benini, Christos Zaffaroni in 2015. They computed the topologically twisted index of ABGM theory, and they showed that it reproduces the entropy of the dual magnetically charged AdS4 black hole. More recently, at the end of 2018, 3 different groups discussed how to microscopically describe the microstates of AdS5 black holes. And now this has been done and extended to all kinds of black holes in AdS4, 5, 6, and 7. And there's at least, there are a lot of new interesting results. And my main point or little contribution that I would like to explain is that you can also find agreement beyond the Larsen limit So the large N limit gives you the big chunk of the entropy, but then there are corrections that we just discussed. There are those that come from quantum corrections, and a particular type of them, we were able to match them to the field theory's answer in different works, in different contexts. So that's what I'm going to talk to you about. So here's a concrete outline. I'm going to talk about the topologically twisted index of 3D n equal 2 Chern-Simons matter theory, but my focus, of course, is beyond large N. Then I will briefly mention the dual black holes. They are magnetically charged asymptotically AdS4, and I will try to explain briefly how we actually compute these logarithmic corrections from quantum supergravity. And then towards the end, I hope to say a little bit about some progress in understanding subleading corrections in AdS4 black hole, in AdS5 black holes, but coming from the superconformal index. So that's sort of my outline. So let me keep moving. So ABGM theory is very well known to everybody in this conference, so I don't have to say much. In fact, Diego did a very nice description, and he had a version of this quiver. So it says Chern-Simons matter theory with these gauge groups and certain matter content. Now, the topologically twisted index would be a partition function on S1 cross S2 with background fluxes. That's essentially the main thing. This flux precisely can cancel the spin connection, and that's why it's twisted in that sense. And now, from the point of view of localization, we can write that partition function using some ingredients. I will not go into a lot of details, again, because I assume most of it is known, but essentially this partition function can be written by including certain blocks. It's like a free partition function. So if you have a gauge field, then you have to add, introducing the partition function a particular term. There's a classical contribution that comes from Chern-Simons. So there's a well-defined algorithm that if you give me the field theory with the quiver and the superpotential, I will write the index for you following this prescription. So in one way to evaluate the index, so here I talk about a contour that I will not discuss so much what this contour is, but technically it's the Jeffrey Kirwan contour of integration. If you follow that contour, and sum over all color fluxes, you end up with essentially a problem in which you have to evaluate some poles. And this is sort of what I wrote here is the answer. Again, the details are not very important. The key thing is that you can just write the answer in terms of solution to this equation. These equations are, of course, naturally called Bethe-Ansatz equation by analogy. We don't understand exactly what, if there's an integrable system behind this. In some cases, it's clear that it is not. But this is essentially the type of equations that you solve, and then you plug in the index, and that's your answer. So now, let me summarize what I just said. So you have a set of equations that is called Bethe-Ansatz because of analogy. You solve those equations, you plug it in the topologically twisted index, and you get an answer. And the important thing here is that this expression is an exact expression in N. So it's not necessarily, the way that you solve, you might want to go to large N to solve using techniques that we know, but in principle, if you solve it numerically, you will have the exact answer in N. And that's essentially sort of where we leverage a little bit the problem. So in the large N limit, everything is more or less as you expected. So these holonomies for the two gauge groups, they have certain scaling with N, and just knowing this scaling is enough for you to compute the leading order. Of course, you can rearrange these eigenvalues using eigenvalue density, but the key point is that, so here the solid line is, of course, the analytic answer in large N, and the dots are the numerical answer. But with that information is enough for you to get this partition function, and from there you can get the entropy of the black hole by a Legendre transformation. This is a grand canonical. But my emphasis is, of course, in the fact that I can numerically pursue this problem, and I can think about fitting how the dependence is on N. In principle, we know the structure of the dependence. So Silvio talked about this correction very nicely yesterday. This one, I don't have much to say, but this is my focus in this talk, is the coefficient of the log. For that, I do a standard fit, and what I can see is that coefficient varying the fugacities in this problem play a role of sort of like interaction in the standard Yang-Yang problem. So you have to vary then and see what the answer of your topologically twisted index. But what you can see from this table is that numerically you're very close to -0.5. So we essentially conclude that after this numerical analysis, the answer for this coefficient is -0.5. Again, the leading coefficient was obtained by Benini, Christoph, and Zaffaroni in 2015. Matches the entropy. This is a prediction from field theory to this logarithmic term. And I want to emphasize that, of course, there are other coefficients like n to the 1/2 that correspond to a string higher curvature correction, which I will not talk about. But again, it's something that we don't have enough control numerically, but it's something that would be a nice question to discuss. All right, so what I just show you, I show you for ABGM, but I have done in this recent paper with Eugene for many quiver theories. So there's a lot of quiver theories that you can generate just by thinking of other Sasaki-Einstein 7 space. So ABGM, let's say, is associated to a 7, but you can think of other 7-dimensional manifolds like B52, N010, M111, Q111. There's a whole list that you can go through, and for all of them, essentially, you can read the coefficient of the log, and you get -0.5. So the question is now that I want to cover briefly is how that number is recovered on the gravity side. So first, let me tell you very generally about these logarithmic terms, and again, they fit very nicely in Silvio's discussion yesterday. They are the one loop term that Silvio mentioned. Okay, these terms, they are determined macroscopically from the massless particle spectrum, and they are fairly insensitive to the UV completion of the theory. So therefore, they provide a sort of a consistent check for any enumeration of quantum black hole microstates. So if you have your favorite quantum gravity that might be disguised as a gauge theory, and you tell me, this is my answer for the quantum entropy, this is the full entropy, and all your terms should come from this, I can check this term and know if you're telling me the truth or not. So it's a little bit like a litmus test. So if you don't coincide, if your answer does not, at this term in your answer does not coincide with what I get from the massless spectrum of the theory, then your answer is not correct. So this has been used of course, recently and before, but Ashok Sen in particular with different collaborators. So he checked many black holes in string theory, in particular Strominger-Baffa in different regimes. And of course, agreement is found. This can be used also as an argument against loop quantum gravity. So if I assume in this conference there are not many people, but again, this is just a test. So if you have a UV answer, I can check whether your UV answer fits my shoe. Of course, more recently, Strominger used this kind of analysis to push a microscopic realization of Kerr CFT, and the sample that really is my inspiration in this job is a work by Bhattacharya, Grassi, Marinho, and Sen, where they essentially knew that for many Chern-Simons matter theories, the free energy goes as an airy function, and therefore you can read this coefficient for a large class. And in this paper, they were able to obtain that term from a supergravity analysis, which is again not very far from what I'm going to tell you. So what I need to do now is to compute this one loop effective action of supergravity. That essentially is a problem of evaluating some determinants. In curve space, the natural ingredient is to use the Higgs kernel, which has one drawback. So it counts both zeros and non-zero modes. So when you want to compute your determinant, you have to subtract whatever zero mode you have. Now, the Seeley-DeWitt coefficient is very well adjusted for problems that you have in curve spaces, because in fact, it's sort of like a diff invariant expansion around flat space. So if you look at the first term in this expression correspond to flat space, t to the minus d over 2. So it admits naturally this sort of Seeley-DeWitt expansion. And so in this little formula, all I want to make sure is that we understand what is the quantum computation I'm doing. I'm interested in understanding what is the logarithmic term. And the logarithmic term here can come from only one coefficient when n equals d over 2. So the logarithmic term come from one particular seedly the weak coefficient that we can compute, and information about how many zero modes I have in the theory. Now, on very general grounds, and this you know by the typical analysis of anomalies, if you are in an odd dimensional space, there's no invariant curvature invariance that you can form. So there's no, this term is zero. But then, of course, you still can have contribution from zero mode, which is what essentially we need to compute. So let me summarize what I said. So there's certain robustness in this computation because it's independent of the cutoff, this coefficient. In odd dimensional spaces, my only job is to focus on boundary modes and zero modes. People call them all kinds of different names, but what I mean is are things that are somehow related to some symmetry that you need to take care of then. Once I know the one loop effective action, I can use thermodynamics to compute the entropy at one loop. And that's essentially my problem. So I tell you what to do with the typical determinants fields that appear. I will also need to have ghosts, particularly if I do this in supergravity, I will have ghosts that come from p-forms in supergravity. So in general, so again, this is just one slide summary of what I need to do. I need to find what are the number of zero modes for a given operator. I subtract them. This is what subtracting them from the heat kernel. Add them with the appropriate scaling, and essentially then maybe look at the ghost contribution. So to quantize a C3 form, I need various type of forms. This is a beautiful work by Warren Siegel in the 80s, but in particular, I needed to form ghost. So it has this funny action because you have to think about this action as coming from, you have Laplacian, but then the gauge transformation act on the Laplacian. So it might look a little bit complicated, but it's very logical once you think of this field as ghosts that you use to gauge fix something that was almost an exact transformation. So the contribution of these two form. So there's also a theorem by Camporesi and Higuchi that in AdS 2M space, you have an M-form zero mode. So in AdS 4, I have a 2-form zero mode. So my goal is to focus on this 2-form zero mode. So basically what I need to know is how many of them I have, and that you can compute using the Euler characteristic, the horizon if it's a sphere, the Euler characteristic is 2, the scaling, there's a formula that you can see by the nature of this to form that scale like this. So let's forget about this G for a moment. And essentially with these ingredients, you get that the gravity reproduces precisely the contribution, the one loop contribution to the entropy that you obtain from the index. Again, I want to emphasize that although I always talk about ABJM, AdS4 cross S7, this is true for any black hole that I can embed in AdS4 cross S7. For all this list, the only thing that I need to make sure is that there's no other zero modes that I can wedge with my 2-form zero mode to make other contribution. In particular, if I check that the first Bethe number of this manifolds is 0, I'm good. Which again, that can be checked in very general things. But again, this is not super impressive, but it's at least a check that the answers that are coming from the topologically twisted index are matching with the black hole entropy even at one loop. All right. So now in the last, I guess, 5 minutes or so that I have, I want to tell you a little bit about these exciting developments for the entropy of AdS5 black holes. So AdS5 black holes have been around for a long time. Gutowski-Real wrote down a solution, and then Chon, Swedish, Lu, and Pop generalized it to a much more general situation, including non-extremal. And people have, of course, tried to compute the entropy, including Juan Maldacena here in the audience. But now recently, there are these 3 seemingly different resolutions to this microscopic counting were proposed by these 3 groups, Cao Bisset, Kasani, Martelli, Murthy from King's College, Choi, Kim, Nangung from Korea, and Benini and Milan from CISA. And so now it looks like for a long time there was no answer to this question. Now you have 3 different answers to the question. So of course, because I'm in the logarithmic police business, I thought, okay, maybe I can check this term and see whether they are talking about the same thing, or maybe secretly, again, it's like a Bohr atom. Maybe you get the energies thinking that the electron is a planet moving around some other planet. So I decided to look at this problem. Again, Luigi's talk is a great help talking about the superconformal index, but very simply is going to count 116 BPS state in n equal 4 or one quarter in other, generic n equal 1 CFT, and then it's decorated with some charges, and there's angular momentum. So again, I don't want to belay this point. There are two approaches, and essentially what happened is that secretly all the papers, secretly all the papers were essentially computing the superconformal index using different approaches. So one approach is, of course, you can think of the superconformal index as a matrix integral, and this is the expression. And if you look at it like this, then the natural thing that comes is to do a matrix model approach. But again, it's technically complicated just because you have this elliptic gamma function. It's not clear which approximation to take. But then essentially, if you take, in this case, if you take one of the fugacities, so in this case, I put the two rotations on S3 to be equal, and the chemical potential for that is tau. If you take tau to be small, then the effective action approach essentially simplifies to something that many people will recognize here, this saddle point equation. I changed some variables. I did a number of trivial redefinition, but this is the Chern-Simon, SUN Chern-Simon matrix model. So therefore, I can essentially compute the index in this limit. So the limit that as I explained is this fugacity for angular velocity very small, and in that case I have an exacting n expression. Another approach to the index, which is more along the lines of this conference, is using a Bethe-Ansatz presentation. In that case, it's very similar to what I show you for ABGM. So the total index would be, this is essentially a Jacobian of going from one kind of coordinates holonomies to another, the ones that appear in the Bethe-Ansatz. The Bethe-Ansatz equation is of course given by this kind of ratio of θ1s. And there's a solution miraculously to this equation, and it's very simple. So the difference between holonomies is essentially a number, and then they are proportional to tau over n. But in any case, you can evaluate using this in the Larsen limit, which we did. But now this is a summary of the results for AdS5. So the answer using the Chern-Simon analogy is exact in n, but it has corrections that are exponentially suppressed in one over tau. It's exponentially suppressed in 1 over tau. And this is the answer, and I can read the logarithmic term here. But you see, I had to pick a specific saddle point and look at that contribution. There are all the saddle points. That's a very beautiful, interesting problem that we don't know much to say. We don't have much to say other than what we wrote in the paper. And the other approach using Bethe-Ansatz approach, so you had a basic solution that gives you a contribution. Then there are other Bethe-Ansatz solutions that we also discuss in the paper, the absolute leading. But at least up to this point, the same logarithmic term. So the main contribution that gives you the leading piece in the saddle point approach is at least at this level, they seem to agree, even though you're taking completely different approximations. So in the paper, we also discuss how to generalize this analysis to arbitrary for d n equal 1, and the answers are there. So you know how to write the index in these two approaches. And interestingly, the answer that comes in this approximation in both approaches is the same. So again, it's log of n, but this time you multiply by the number of vector multiplets in your quiver. So let me conclude with a few open problems. So clearly, I just show you the field theory side for type 2 for n equal 4. It would be nice to try to do the computation on the gravity side. This is a little bit more complicated now. I'm working on that with my student Marina David. And of course, now we are in an even dimensional space. So the computation now has contributions that come like dynamical, I would say, and then other contributions. So, but that's another thing that I did not talk about here is higher curvature corrections. We have some understanding of what's going on in ABGM, but this is again not super clean. This is not just turning the crank. So there could be a lot of interesting physics in this approach because that relates. So there's a precedent by Maldacen, Strominger, and Witten for M5 brane in asymptotically flat cases. But this is sort of a door to understanding wall entropy and many other interesting questions. And I'm working on that with a postdoc from ICTS, Joel Gosh. So the n equal 4 answer is quite interesting, because if it is really given by the index and the index is independent of couplings, so then you have the very powerful answer or implication that there could be no higher derivative corrections to the entropy of supersymmetric black hole. So that's something, again, that deserves a lot of attention. Another avenue that I have been following, some of the results I presented in this paper with Marina and Junyan, are essentially that, in fact, as impressive as we are by this UV counting, a lot of the counting for AdS 4, 5, 6, and 7 can be done by just going near horizon, exploiting symmetries, looking at asymptotic symmetries a little bit, following curse AdS CFT. So this is, of course, I don't take as a negative, right? So that means that in all the structures that we have in field theory, there's something universal that we have yet to explore. And I would like to finish with some integrability connection and saying that, as you can see, a lot of these problems are essentially problems about Bethe-Ansatz equations, but certainly for the topologically twisted index and for the superconformal index. And clearly understanding the space of Bethe-Ansatz solutions and as function of fugacities, they are like interaction, is equivalent to really understanding different phases that we can have in quantum gravity. So with that, I thank you very much.
Thank you, Leo. Pedro, you have a question, yeah?
Yeah, just a technical question. So the log n, from the point of view of summing over beta solutions, comes from the sum, or is there a solution that dominates? Well, where is mathematically, where is the log n coming from in this sum?
So mathematically, it comes from the degeneracy of the dominant solution. So this the basic beta solutions.
So it's one solution of the bit equations that gives the log n.
Yes. Yes.
I see. And do the other solutions also have a physical meaning? For example, in gravity?
Right. So the phase space of solution is quite interesting. It depends on these fugacities where you are. So, for example, this solution that I show you, this basic one, essentially distributes holonomy more or less uniformly. You can distribute them in centers, like have a center with, you know, and that actually is subdominant in some region of fugacities, but then becomes dominant in other region of fugacities. If you compute the logarithmic term from them when they are dominant, it also gives you log of n divided by c, where c is the number of centers. So it looks like, yeah, it looks like you can go as right now we don't have complete control, but whenever we can go to different regimes, we see that log of n appears for different reasons, but it appears.
So say in the context that I'm more used to, when we solve bit equations, sometimes we have these roots, the solutions of bit equation form these different segments, different domains. This appears a lot in n equals 4, say, which would correspond to the various ways of exciting the string. And here, do you also have various solutions of the Bethe-Ansatz, and will they correspond to having more than one black hole or something like that, or?
Right. So this is a part that this is sort of my wishful. This is my wish list. So we know. I mean, we know that this space is very complicated. The space of quantum gravity. So the phase space. So there could be. Yesterday or the other day, Luigi was talking about the deconfined phase or a slowly confined. So all of this you should be able to see in the dynamics of the Bethe-Ansatz equation. Now we are not there yet, but this is sort of like a really nice problem to try to see all these corners of multi-center black holes, small black holes. If they are in the index, we should be able to see it by understanding when they are dominant.
Mm-hmm. Thank you.
Right. I see Shota has a question.
Yeah, okay. Yeah, I can do that. Yeah, it might be related to this third point that you wrote, but in the matrix model approach, do you see any signs of interest in double scaling limit?
Right. So yeah. Okay. So in the matrix model, so people, okay, unfortunately, there's not a lot of analysis. So people try to go to the limit. For example, in ABJM, we're interested in the M theory limit. So k equal 1 and large, and that's all that, you know, that's where people go and dig. This is the lamppost. So I have tried to analyze what happens, let's say, in the Hoff limit. So again, the leading piece is not interesting. There are corrections that become a little bit more interesting, but again, not very systematic. Okay, so I'm not aware of any systematic approach that goes and tries to understand what's going on. Yeah.
I see. I was just wondering if there is something similar, like old matrix model story, like you take some you scale various like a chemical potential and take n to large and see some like universal behavior, but I guess
no,
like not much is known, right?
I don't know.
Okay, thanks.
I guess I don't see. Oh, yeah, I don't see any more questions. So let's thank Leo again.
I think Vladia has a question.
Where? Who?
Vladia Kazakov.
Oh, okay.
I just show my hand in the picture.
Yeah. Okay.
Very short question. Are these beta equations related somehow to this Nekrasov-Shatashvili beta ansatz which appear?
Absolutely, yes. I mean, all the jargon goes back to Nekrasov-Shatashvili, how this beta vacua, and yes, it's absolutely that. Of course, this is in a slightly different context, but it's really borrowed strictly from that. Yes.
Thank you.
All right. Now, nobody else who has a question, right? Okay. All right. So, so let's thank Leo again. And Gustavo, next speaker is Gustavo. Can you put up your slides?
Yes.